the presentations, you learn something new even in basic presentations, but the hallway track is just indispensable.
So I think we can get started. I'll probably need a great part of this hour, so let's talk a little bit about C++ modules. It's now 2025, we're closing into C++ 26. We had a revision of modules in C++ 23, we had them coming out in C++ 20, and discussion for over 10 years about modules. So, well, what is the state about them? Let's check it out. And a little bit about me. I'm Alexsandro Thomas. I'm a senior software engineer, currently based in Norway. I'm a languages nerd, both programming and natural languages, so feel free to talk to me about that. And also I'm a GPU enthusiast. And I've been dabbling in tooling recently in my company. And that led me to think about, well, we have this new technology coming out that is modules. How can we get to leverage that? What is the capabilities? Can we get to utilize them fully already? So let's talk about it. But to start off, I would like to mention and just give an introduction about why do we need modules. I feel like there's a lot of talk about what modules are, but contextualizing why they came to be in the first place is a very good idea. So let's step back a little bit and look at a very simple C++ program. This is one of the most simple programs I can think of. You just have your function foo that takes in an x, returns x minus 42, and your main function that calls x, everything is fine. And if you take a look at your compilation flow, you're going to see that you just call the compilation for your main program, and then you call the linker, and you get an executable. But programmers are creatures that like compartmentalizing their code a lot. So one thing that is very common to do is to move different things into different files. So in the end, you might end up with something like this. You have your main.cpp and your lib.cpp, but they are different.
Is it possible to turn up the brightness? Because I'm in the front row and I can't see anything of what's going on the screen.
I can try to do light mode.
Yeah, thank you.
Yeah? All right. So if we have a code like this, you can try to compile it, but, well, suddenly we get an error. And the main reason is that your compiler doesn't know what foo is when it's looking at main.cpp, right? And then what we can do is tell the compiler, hey, I promise you, I will give you a foo function that takes in an x, just trust me. And if you want to be pedantic and you also want to avoid your compiler screaming at you that there's no missing prototype, you can add it to the lib.cpp as well. Well, our compilation flow looks like this right now. You can compile your lib and your main independently, and then the thing that will tie them together is the linker. And that will look at the definitions for everything and make your executable work. So in the multiple source C++ programs, you end up with your source files being turned into this magical thing called translation units that I'll come back to later. And then every name has to be declared in every translation unit that it's used. And the linkers is what is responsible for finding the suitable definitions, and inconsistencies will cause errors or unintended behavior. And we can take a look at that. Suppose that now we want to increment this function. So now it can take a different parameter. This y will be a default parameter for the tube, but it can be changed. And then main.cpp, now when it tries to use that, your linker will no longer be able to compile this because we promised that we would give it a function that takes in an integer, and we actually just compiled a function that took in 2 integers. So how can we fix this? Well, we just create a third file that contains this one part that is repeated into all of your source files. And then you use this include, which basically tells the compiler, please do a glorified copy and paste of whatever is in this lib. Amazing technology. Well, anyways, this works and has worked for years. So, and the compilation flow will look something like this. You have your lib being indirectly used in your main.cpp and lib.cpp, but it does not affect the compilation commands. It's just there and your compiler knows what to do with it. But then we get into something called the one definition rule. You get that every name must be declared in every translation unit that is used. I said this before, but any entity must be defined exactly once, and the consequence of that is that there can be only one definition in any one of the translation units in your code. And well, just to quote Bjarne, every word in the C and C++ definitions about ODR are there to work around the fact that we cannot identify the one true definition and have to compare definitions instead. So I'm not going to stand here and give you one more definition to compare. I'm just going to try to show you an example. So let's take a look at this flow. We have two headers, one depending on the other, and then both of them get utilized in our main.cpp. So how can we deal with that? Our point header just has a struct point. Beautiful. There's nothing wrong with that. Our rectangle header includes your point and then creates a struct rectangle which builds on top of that point. And then our main.cpp includes both of these files and then instantiates both of these objects. And this is very interesting. Let's take a closer look at what the compiler is actually doing when we have this. So the first thing that you will do when you're pre-processing this file is that you will expand the header. So let's expand this rectangle.h. And then you get the contents of that. And then let's expand your point.h. And then you get that. Well, I see something interesting here. Your compiler will complain to you. And the reason is that you're redefining struct point. And it's very easy to see it here when you have your translation unit, which is what happens after you combine your headers in your source files. But it's not that clear to see when you just have your include statements in your program. But coming back to what we had before, that's something that we can fix. C++ engineers and C engineers are very smart, so they created an amazing syntax to fix this. Oh, that's lovely. But I mean, we came a long way since the C days, so we can do better, right? Pragma once. That's beautiful. Well, let's just pretend a little bit here. Let's say that point.h header is now the de facto point header. Everyone uses it. I mean, you don't need any other point struct ever. It's just perfect. So you can imagine a program that has the following structure. You have your main program. It has two third-party libraries. It depends on your point lib directly, and then a math lib that also depends on point lib. So you have that point lib repeated twice, so the header is repeated twice. And if you take a look at the contents of those files, you can see that our main.cpp includes both of these headers, and our math lib includes the point header, but we are smart here. Everything has pragma once. We're not going to repeat the definitions, right? Let's compile this program. Well, this doesn't really compile. And the reason is the compiler cannot really tell apart these two different files sometimes. It can try to do some heuristics, but these I tested on MSVC. Clang also doesn't really seem to be able to compile this program, and GCC, congratulations, they're able to tell that it's the same file. Even if the hash is the same, the other compilers are just not able to tell them apart. But just some considerations here. I'm not trying to scare you away from using pragma once. They are not standard, but they are widely supported. And the compilers do use some heuristics like file size, modification time, and file content to be able to tell them apart and know that it's the same file or not. And also for the header guards, the old style to do this, the compilers can optimize invoking the preprocessor, so it's not as slow as you might come to think it is. So yeah, you shouldn't really be afraid of using any of this. But then we got a great quote by Bjarne again. Header files are a major source of complexity, errors caused by dependencies, and slow compilation. Let's take a look at why. Coming back to our code, let's pretend that we just forgot to include our point header. Do you think that this code will compile? It does compile. And the reason is that our point header is included before in our main.cpp, so everything will work. But now, let's switch the order. Does this compile? So this is a huge problem with headers. You cannot really know if a header is complete or not before you include it in a CPP file and you compile it. But you might have many headers and many CPP files in your program, so there's no way to guarantee that something is complete unless you just compile that alone. So I tried to search what shouldn't be in a header, and I landed upon a page by Microsoft Learn that gave me a list of a few elements. So let's break down each one of them step by step. The first thing that they say that isn't really a good idea to put in the headers are built-in type definitions at namespace or global scope. That's a mouthful, and to be honest, it's very incomprehensible in my opinion, but let's try to break it down into what it can mean. One thing that it can mean is that aliasing built-in types isn't allowed, but that's obvious. It doesn't work not only just in the headers, it doesn't work even in a CPP file. You can't try to redefine your built-in types as structs or something like this. Also, define directives can be very bad practice in headers, and that is true. If you have something like this where you're trying to define your int as an int64t, which is a quite standard if you're doing something like competitive programming, you're just trying to get something going. If you leave that in the header, whenever you try to compile, your compiler can complain to you that your main must return an integer. So that will not work. And also, it can also mean that aliases can produce unexpected behavior. If we look at this example where we're using this user ID and product ID as just simple aliases of integers, and then you have your void process, which takes one of each, and your main.cpp includes that header and then instantiates 2 of those types and then tries to call them in the wrong order, your compiler will not do anything to tell you because it's not a strong type, it's just an alias. You're basically just calling an integer by a different name. So you should be aware if you're using that it may not provide all the guarantees that you expect it to. And then the other thing that Microsoft recommends not putting in a header is non-inline function definitions. And that's also clear why. So let's take a look at this header. You have your struct point definition here. You have a print point function that is defined in the header, not only declared. And you have your add points function that is just declared. Then you have a lib.cpp, which includes this header and then defines that other function. And a main.cpp that includes that lib header and then tries to make use of the functions that are declared there. If you try to compile this, what will happen?
It works.
It works. Everything is fine. But now if you try to link this, what will happen? Multiple definition of print point. And the reason for that is that both of your source files will now have a copy of this definition of this print point thing. So it's a very bad idea to keep that. Well, it's not impossible to fix that in a header. If you really want to keep your code there, you can just, for example, add inline there, or just do the right thing and put your code in the CPP file. For non-const variable definitions, you get a similar situation. When you try to compile multiple files using that and then link them together, your linker is going to tell you that there are multiple definitions of variable. And the reason is that every translation unit that is included in that header gets its own copy of the variable, and that's an ODR violation. Aggregate definitions, your beautiful types that are defined with the aggregate constructor, they also get the same problem. If you try to link that, there will be multiple definitions in the multiple files, because every translation unit gets its own copy, and that's an ODR violation. For your unnamed namespaces, that can be a problem because it's a very common copy-paste mistake when you're moving stuff from a CPP file that you can want to generalize and use somewhere else. And every translation unit that is included in this header gets its own copy of the function definition, and that is a binary bloat. It's not really an ODR violation. The only thing that's happening is that you get a copy of this function with internal linkage in all of your files, and that's probably not what you really want to do. Your binaries will increase for no reason, basically. And your using directives are also something that is not recommended, and that's clear why, because that pollutes the global namespace. And every transitive header now becomes problematic. So anything including this header also becomes part of the problem now. And that will increase the chance of name collisions. Not really if you're just using namespace STD, but if you're using every namespace in your application, you might get a lot of problems. So introducing modules, a novel approach to code organization in C++. And that's not me telling that to you. If you look at the page, for example, from Microsoft Learn, they say that in Visual Studio 2019, the C++20 modules feature is introduced as an improvement and eventual replacement for header files. That's a strong claim. So what is that? Let me just disambiguate for a while. The term module can be ambiguous if you've been looking around the C++ community for a while. It can mean a Clang header module. It can mean an Objective-C module. It can mean a standard C++ module, which is what we want to look at here. But even that can be divided between named modules and header units. For the context of this talk, if we don't specify which one we're talking about the named modules. So modules in C++ are this tool for consuming external code by packaging components and encapsulating their implementations, and also they're designed to coexist, but minimize the reliance on the preprocessor. And it has some fundamental goals, for example, componentialization, which is just to make single components be logically grouped, isolation from macros, to provide a strict boundary for where all of your macros can propagate to, scalable builds by avoiding redundant reparsing of your headers, and also support for modern semantic-aware developer tools by having well-structured, machine-readable representation of the program entities that all your tools can use to provide you better insights of what your code is doing. So if we look back at what we had before at conceptual representation of a build flow, what we want to get to, essentially, would be something like this. You have one file that is used by your source files that include it, and it can also directly generate an object file. So that's the conceptual idea of what we want to get to. So how we do that is if you take, for example, this lib.h header, which just has a point, a function to add points, and then the CPP file that includes that header and defines that, the equivalent in a header would be something like this. You export this lib module, you export the definition of the struct point, and you export this add points function. And that should be enough to cover both of these use cases. So if we break down what a module really is that you have one or more module units, and that's what defines your whole package. And they will typically start with a module definition. So they will have an optional export keyword, this module keyword, the name of the module, and this optional partition. So they're special kind of translation units. They're not exposed outside of the module, and they can either be an interface or an implementation unit. And they can also be broken down into partitions. We'll get to that. And when we get the complete package of all of your module units, you will compile those and generate what's called a built module interface, which will provide this efficient representation of what the module is exporting to the rest of the program. So if we take a look at the difference between the interface and implementation units, that's really simple. If you have an export definition, that is an interface unit, and if you don't, that's an implementation unit. Very easy to distinguish. And your partitions are just tools to allow splitting the interface or the implementation of the module into different files. So here we, for example, have this module geometry. We have a circle that is just split from the main thing. We have your helper module unit to get some helper functions. And then you can import that helper and you can re-export that interface as part of the main interface of the header. So I lied a little bit. This is what we get to. A module is this logical component that groups a lot of things together, but they provide this unified interface. Everything outside of the module doesn't see really what it's composed of. They just say that they want to utilize this lib module, and then this lib module, when it's compiled, it generates your object files that can get linked by the program. So it's basically a tool for the developer to compartmentalize a lot of things and then expose a very simple interface to that. So if we get an overview of the module units, if we permutate between interface or implementation units and partition or non-partition units, we basically get 4 different types of module units. And they are this. So the primary module interface unit is just an interface module unit without a partition. And every module must contain exactly one of these. So that's the most common one as well, because you can have modules that just have this one. A module implementation unit are implementation module units without a partition. And they're just very useful tools for splitting interfaces and implementations. And they will implicitly perform an import of the module. So if you just have declarations in your module, here's where you can define the corresponding declarations. The partition interface units are just tools for you to separate large interfaces into multiple files. So if you have a very large interface for your component, you can split that into multiple files. And they must be transitively exported by the primary unit. So for every one of your interfaces, you must have this export-import syntax, which is a little bit weird, but you get used to it. And then you also have these internal module partition units, which are your implementation units with a partition. And they're just useful for keeping some utility functions and breaking some dependency chains, but they're not part of the external interface of the module. So there's also 2 fragments, as they're called, which help you do different things with modules. So the first one is this private module fragment. And if you've ever written library C++ code, you know that writing a header is a little bit of an art. You need to write everything in a way that your customer or your users will be able to read and parse what exactly that component is offering in terms of logic for your program. But this would look very ugly. If you have all your definitions in the same place as your declarations, it would be very difficult to just browse a list of what is exposed. So what this does is expose this small little part of the program that you can use to just move everything that is an implementation unit, and then you have this very clear, very simple part where you just list your declarations. So you have a part that is very easy to read and a part that is easy to implement on without having 2 different files. They can only really be part of the primary module interface unit though, and they're only really for modules with a single module unit, so they're just a very useful tool if you don't want to split it in a module into multiple files. The global module fragment serves a different purpose, and what it does is help you do something like this. So if you need to include vector and print, for example, if you try to do it in the main part of the module, your compiler will even tell you that this include appears erroneous, and the reason is that everything that you're putting here is treated as something that you want to export as part of the module. So the global module fragment adds a tool for you to just move everything into a place that is not part of the interface or the purview, as it's called, of the module, and you just import everything you want or use any preprocessor definition that you want. They are especially useful when the headers are not able to be made into a module because of macros. And it's also important to know that non-referenced entities are discarded. And then your header units are also something interesting because you can think, what is really importing a header? Because you have all your header code from legacy C++ code bases. So a header unit basically just allows you to import those headers. There are translation units formed by synthesizing an importable header. By the way, that's an implementation-defined concept, so I have no idea what to tell you what exactly that means. But all the declarations are implicitly exported, so you don't need to go into your headers, just mark everything as exported for you to be able to utilize it when you import them. And they provide basically just all of the module benefits, but for the legacy headers that you have in your code base. One thing that they restrict you to, though, is that they don't allow external definitions. So if you have something like this in your code and you try to compile it, you will get an error saying that non-inline external definitions are not permitted in C++ header units. And the easy way to fix it is just add inline in that. So if you really want to have this anti-pattern of keeping your definitions in the headers for some reason, then just mark them as inline. And also it's important to know that macros are made visible with a caveat. So if we look at this full legacy header, and we have a definition of foo version, and then this foo function that is defined, and then we have this foo module that exports, imports that header, so it forwards the import of this header unit, and then you have this function there that uses this foo version macro, that will compile just fine because the first thing that imports your foo legacy module unit, header unit, will work successfully. But even though you're importing it, that macro will not really be re-exported. So only if the foo function will be visible outside of the context of this foo.cppm that imported it in the first place. The STL header units are the most amazing feature that came with C++ 20 because they just defined the importable C++ library headers for the STL. So that just means that you could take all of your includes that you had in your program and substitute them with imports and just get the same benefits as you would have before. And C++ 23 introduced an even more amazing feature. If you had all of these includes and then you have all of this cognitive overload of having to remember which functions are defined in which header, what you can do is just import std, and you have all of the definitions in the std namespace available to you. It just exposes all the symbols. There's also the std.compat module that additionally exposes the C global namespace declaration. So if you use printf from C++ for whatever reason, you can do that. And also it's important to know that your macros will not be re-exported. So if you need something like assert from cassert, that will not be part of this. So you would have to just import cassert or include cassert. But let's compare the traditional headers versus modules, because now we know what both are, but what are really the differences? And for that, I would like to circle back to headers. So taking our example from before, where we had our point, our rectangle, and our main file, now if we move that to be in modules, that's much better. You just export whatever you want to make available from the interface of your modules, and then it doesn't matter in your main.cpp if you will change the order. And also in your rectangle.cpp, if you forget to import point, whenever you're compiling that rectangle module, your compiler will tell you, there's something missing here. I don't have this definition, so you solve that problem of the import ordering mattering. And if we look back at the recommendations that Microsoft gave of what not to put in a header, the first thing that was there that you couldn't really define your basic types to something else because you could get an error like this where main couldn't compile. Now you can do that with a module because you can just define something like your int to be an int64t, make use of integers as if they were int64s in your module, and then in your main you can import it and it doesn't affect anything. That's not re-exported.
Is
The non-inline function definitions are similar. If you change it to a module, you just export whatever you want, and then you don't have any problems with that. The definitions can be part of the modules. Non-const variable definitions, same thing, just export them. If you export, the semantics will be correct. It will not just be an accident what's happening. Aggregate definitions in the same manner, just export whatever you want to make available outside, and it will work. And unnamed namespaces are interesting because, of course, that will work if you just make it into a module and then you can use this anonymous namespace function. But if you try to do something wrong, like exporting this internal symbol, your compiler can actually help you. So it will tell you that you cannot export this anonymous namespace do something symbol because it has external linkage. This is even a good error message, which is very surprising in the C++ compiler ecosystem. Use interactives are also fine because now when you do it in the context of a header, everything will just work. You don't really need to worry about this user namespace leaking out unless you really export this user namespace. And also one thing that is really important to keep aware is that there's a lot of dependency chaining and breaking in C++ whenever you want to make a large code base. And one example for that is to make, for example, a Pimpl idiom. So if we take a look at this private header that we don't want to make available to any users, you define this secret macro and then we use it inside of this secret function. Whenever we're using this user-facing.th file, we can just create a user-facing class that has this getNumber function and then some Pimpl structure. And then in your user-facing.cpp, here you can actually import this private.h header. And the user will not really be able to see because it doesn't cross to the header boundary. And then you can just start your user-facing class by creating this internal object, start your internal implementation object by making use of that function that was defined in private, and also create your getNumber function in terms of that Pimpl. So effectively, you give access to the users of user-facing of everything that was in private without exposing that dependency. With modules, that's very different because if we have the same header but now as a module, private.cppm, and then you export this module private, you have your macro definition, and then you export this secret function, and then in your user-facing.cpp, you export your module, and you import private, but you don't re-export it. Now you can just export this user-facing class that has an impl, and you don't export this impl, and then you broke your dependency because the users don't really have to know what is that. Well, small caveat, that doesn't really work with every compiler. MSVC is the only compiler that I got this to work after deleting the interface file for private.cppm. So GCC and Clang currently expect that interface file to be present even though you're not directly depending on it. So you can do something similar, which is just having a file that will be the main interface for that module, and then you export it, you export all of your class and your Pimpl infrastructure, and then you have a different file that will be basically implementing that. So there you import your private, and then you have whatever is needed for a Pimpl. That looks like something I've seen before. That's basically just what you did with headers, but well, that's just what you have to do. While we don't really get a full modules support with the dependency breaking, that's just what you may have to do. And let's take a look a little bit at compile time performance, because that's one of the big selling points for modules. You're going to speed up your builds. And for that, we can compare it with a hello world.cpp program that just needs the IO stream header, and your mix.cpp file that requires 9 of the standard headers and just perform some operations with them. And then you have this allstd.h, which is just a file that includes all of the headers from the standard library. And this is actually taken from a paper from Bjarne, if I remember correctly, that was proposing adding the import std to the standard. So let's look at what happens. So just taking a look at the basic files, when you just include whatever you need and then compile that, you get compilation times like this. And that's on MSVC, if I remember correctly. So you're going to get the compilation time that is bigger on the file that needs more code. That's obvious, but a smaller one in the hello world. And if you include all of your headers, just include everything. Don't really think about what you need, just include everything so you don't have to remember. Now it grows a lot. And that really just goes to show at what is really the bottleneck of compilation times in C++, because if you include everything, you get a very similar compilation times for the function that needs a lot of code and for the function that doesn't need a lot of code. If we import the necessary header units though, so instead of including them, you just import them, that's a much lower time. So it's faster on both situations to just include whatever, import whatever you need and include whatever you need. And importing everything doesn't come with a lot of a penalty for that as well. In both scenarios, importing everything is still faster than just including what you need. And if you import std, which is the new standardized way of doing this, that is amazing. You just get the shortest compilation time of all of them. So you don't really need to worry about anything anymore. You just get the best compilation times for getting everything you need. You don't need to compartmentalize anything. But, well, this is for MSVC and on an old paper, so I wanted to benchmark that myself. And on GCC, you get a figure like that. You can see that just importing what you need is faster for the Hello World program, and then importing std ends up being the fastest one on Mix. And on Clang, the fastest one ends up being import all, and then importing std. But the difference is not really that big. So, well, it's still just importing std seems to be the best option and the most portable option for you to do. And there's a small note here. I can hear in the back of the room someone's thinking already, well, I could achieve this before with precompiled headers, or I could achieve this before with jumbo builds. Well, that might be true, but modules are standardized and accessible by every C++ developer. And every getting started guide in the future can provide this. So that means that it's a portable performance gain. You can write the same code, just go to different compilers, different build systems, and everything will have great performance because that's just a standard way of getting good performance for compilations. So you solve some of your problems with headers by using modules. You have a structured semantic import mechanism. The component interfaces are now compiled independently, so you don't need to just repeat the compilation of them every time that you need to use them, because they're processed only once into an efficient binary representation, and they also provide a very strong isolation from your macros. There will be no global pollution. But let's take a look at how the compiler support landscape is. And if you go to CppReference.com, you get a figure like this. You get that your GCC and Clang is partially implemented and MSVC is fully implemented. But what exactly does this mean? This doesn't tell me much about what can I use or what I cannot use. So I wanted to do some feature testing, and I will explore all of these components and just break down what is supported and what is not. And if you take a look at what I used to do this testing, this is nothing crazy. I didn't go to build Clang or GCC from trunk. I just use the version that is available on the latest Fedora, if I remember correctly. So that's something that should be easily accessible by every developer. So the workflow that I wanted to do for feature testing is just compiling the code and then compiling a simple test that would verify that our getAnswer function would be equals to 42. So for named modules, that's the simplest. Just export this integer getAnswer. So return 42. It works on every compiler. That's fine. Header units, you just define this macro 42 and then utilize this macro 42 in the getAnswer function. That will work on every compiler. The test will pass, but Clang will issue a warning saying that the implementation of header units is in an experimental phase. Global module fragments, which allow you to include headers and then make use of whatever functions were defined there below, also work on every compiler, so you can also make use of that. Private module fragments that just allow you to break the declarations and definitions do not work on GCC. And I feel like for the first time in my career, I had the compiler saying sorry to me instead of me saying sorry to the compiler. So that's great. Module implementation units are similar to what a private module fragment does, but this actually happens to work on every compiler, so you can still do that, but just not in the same file. The module partition interface units that just allow you to separate the interfaces, so you can put this getAnswer function in another file and then re-export it. That works on every compiler as well, no problems there. And the internal module partition units that just allow you to have, for example, this helper function that returns 42 that is called by this main function also works successfully on every compiler. So this is something that is a little bit more understandable in my opinion. You get that most things are supported by most compilers, with the exception of Clang just issuing a warning that header units might not be right there yet, and GCC not supporting the private module fragments. And if we look at the standard library modules, Also, if you go to CppReference.com, you get these very confusing lines just saying that Clang libcpp doesn't support STL header units at all, and then GCC supports everything partially, Clang supports STD module partially, and Microsoft supports everything. So let's take a look at what exactly does this mean. And for that, let's do some testing using that same mix.cpp file that we had before that just includes 9 headers and makes use of them. So if we just define this std.cpp.h file that has every single header from the STL in that, and then you just import it as a header unit, you get that to work with everything, but Clang is just issuing a warning that something might break, but it just works. For the header units, if you just, in your mix.cpp itself, try to import everything, now you get a problem with Clang. It will start issuing some warnings that the declarations are ambiguous, and I might have just have been doing something wrong, but that means that other people might do the same wrong things. So yeah, it's not really right there yet, the implementation. And for the STD module, just import STD and do whatever you want in your mix.cpp file. That also works on every compiler. So we got a matrix like this. Clang seems to be the one that's the most lacking behind in terms of exposing your header units, but the STD module, which is just a better replacement for the STD header units, just seem to work everywhere. So the main thing is that the libraries do provide these module definitions for STD and std.compat, all of them, but the users have to compile them themselves. So it's not that easy to use, but if you want to pause back on the recording or on the slides and look back, I happen to compile all of the commands, and all of them work fine if you just put that in your build scripts. For the compiler interoperability, we have a bit of a problem. There are a lot of variations among the compilers. I've been using, for example, the Clang convention, but MSVC, Clang, and GCC do not really agree on what the file types should really be for modules, although you can tell them to use another file and treat it as a module. And also the APIs are not really the same. So they will be differing per compiler, and that means that you cannot really compile a module with one compiler and then use them in the other one. And also you get some consistency requirements now, because your compilers are very strict with checking the compiler options, for example. So whenever you want to utilize a module that was built with a certain C++ dialect, for example, C++23, and the file that imports that has to be the same dialect or the same optimization level. The source file's consistency is also a little bit of a limiting factor now, because that says that all of the source files that were used to produce a built module interface have to be present whenever you're importing that. And every compiler seems to really be depending on that right now, so you can't really just ship a built module interface without the source files that were used to create it. And the object definition consistency is also something that they enforce, but that's not really bad. That just means that whenever you're importing something, now the compiler, because it's semantically able to check everything, it can tell you that the definitions do not break the one definition rule. So when it comes to build system and tooling, I feel like that's a very important concept to talk about whenever talking about C++, because I don't know anyone that is building all of their 1,000 files library by writing compile commands by hand. So let's just propose something like we have a lib geometry that has a point, a rectangle, a square, and a circle. We have a main, and then lib geometry is utilized by main. Then you get something like this. That's very intimidating, but we can break it down into components. We just have our headers on the left side. We have our sources that are compiled independently because they just need the headers to compile. And then the only thing that really needs this ordering before being compiled is that the binaries need to be only generated after the source files are compiled into objects, and then main also needs the lib geometry to be compiled first before linking into it. And that's what's called an embarrassingly parallel build, because everything can basically just be compiled at the same time. But with the modules, the situation changes a little bit, because now you first have to compile everything before everything that depends on it has to be compiled. So basically, your build system has to generate all of these directed acyclic graph of the compilation and do it in order. So it's no longer really massively parallel, but at the same time, do you really want something that's compiling a lot of things at the same time, but just wasting computational resources? That's a question that you have to answer for yourself. But then things are a little bit more difficult now. So first of all, we can discuss if rectangles are squares later, or if squares are rectangles later, but the main thing here is that we are exporting a square module, and then re-exporting this rectangle from its interface. So now we have to scan the dependencies, and the compilers provide a tool to do that. So when it's scanning this file, it can tell you the primary output of this file will be square.o. It will provide this logical component named square, and then it depends on this logical name component called rectangle. And then your build system can utilize this information to search for what is needed. And we can take a look at, for example, how CMake does that, which in version 3.38, they added native support for named modules. Not really header units, so if you want to use that, you have to add support for yourself. And that's supported on both the Ninja and Visual Studio generator. So rest in peace, Makefiles, but at least you get support for something. So if you look at this file, the first thing you define is that you need the version 3.28. You define the standard version that you need, and of course you need at least 20 to be able to use modules. And when you add the library, you need to get used to this bit of an arcane syntax to define what you want to export from that. But you can basically say that you have this file set of type C++ modules that has this lib.cppm file, and also you have your implementation file. So you just specify the sources in a different format than what you normally do with a CMake program, but that's just the new syntax. But then whenever you're adding something that depends on those modules, you can simply just say add the executable and link to that library, and everything will just work as expected. And how this looks on the build tree is that first CMake will have to scan all of those files for dependencies. Then it generates this dynamic dependencies file that gets used to know how to order these builds. Then you can, in order, as they're needed, build all of these files and then link them together to your executables. And then also in version 3.30, CMake added experimental support for importing STD, but, well, you have to add this very beautiful string that you need to mine from the source code of CMake if you want to utilize. So it's not really production ready yet, and it's very difficult to maintain in your build system, but you can already start experimenting with it. And how it works now is that you can just say, add executable main, and as long as you have all of the scaffolding enabled, it will just work. And how it does that is by just doing all of the work needed to get this STD module compiled, and then just injecting that structure whenever it detects that you're using that in any file. And also dependency managers, they are a very important tool for C++ developers because they perform a bunch of very useful functionality. For example, automatically retrieving libraries from remote repositories, performing transitive dependency handling. So if a library depends on something, it will also go and fetch that for you. Cross-platform consistency, so that you can get the same code working on different platforms with the same libraries. Build integration, to just allow you to utilize your favorite build system with the dependency manager, and also binary caching to speed up builds by not having to build every dependency every time. With modules, that's especially useful because they need to do all of these last three options even more, because they need to make sure that all of these build module interfaces will work across different systems or compilers. It needs to integrate into the build system to tell the build system, I'm exporting these modules, and it needs to do this binary caching of this special type of binaries that are the build module interfaces. And you basically have three options as to how you can basically utilize this help from the dependency managers. The first option would just be to wrap non-module libraries with a module adapter, and that would look something like this. Your dependency manager just fetches a library for you, and then you yourself maintain a module wrapper for this library that just exports everything you need from there. But then someone might be saying, but FMD has a module themselves, you can just utilize that. And that's right, so the option 2 is to just ship module interface sources. So as long as your library is exporting these module definitions for you, you can probably ask your dependency manager to just give that to your program, and then you compile it yourself and utilize it. And the third option, which is the best in terms of usability, is just tell your dependency manager to fetch that lib. It will fetch a lib, compile that module, and then just give you the ability to import the library that you want to utilize. But there's a problem here. All of this process can easily become very platform-specific, difficult to maintain, and error-prone if you're doing it yourself. And you really need better first-class support from tools, because currently, only really the first option is what you can achieve. But even achieving the first option is very difficult. I very deterministically created this graph showing my journey through trying to get all of these three options working, so I don't recommend it. Adopting modules in projects is the next important topic that I would like to cover because, of course, if you can do it from the beginning, that's the easiest way. So if you have a new project, you have recommendations from big projects, for example, Clang saying it is best for new code and libraries to use modules from the start if it's possible. Or Microsoft Learn saying we recommend that you use modules in new projects rather than header files as much as possible. And there are some real advantages to that. For example, if you adopt the module early, it will be minimizing the transition cost in the future. You also get all of the future improvements that will come to modules and modules tooling for basically free because you're already using modules. And also your code can from the beginning be structured for modules. So you can define very good rules in your project for how to place those files. But the choice isn't really always clear for existing projects. Most projects will not really rewrite everything at once, and the build system support increment will be required. So if you have a very complicated CMake system, it might be very difficult to get everything to work. And also you need to get all of your lazy developers in your company to learn this new type of library, so, well, that might be difficult. And there are other build time strategies that might be better suited for your project in specific, so you should probably take a look at precompiled headers or Unity builds if you just want to get some good build benefits, but without having to change anything about your code. Also, you should really consider using header units to bridge the legacy headers and modern code, because they just provide this modern access to the legacy headers, and there's no code change that is required. But there's still experimental support on some of the compilers, and there's a lack of build system support. So CMake, the biggest build system, doesn't really support utilizing that. And also you should be aware that macro-heavy headers will work, so if you need to utilize any macros to configure the interface that a header will be adding to you or exporting to you, that might be very difficult to get to work. So I think that overall, the best option for existing projects would be incremental adoption. You just move step by step by maybe starting with some utility libraries or some self-contained components that you can write in modules. You can gradually convert something that is commonly used into modules to get more experienced with how it is to utilize those. And of course, first experiment with internal-only modules before exposing them both to customers or just other teams in your company, because otherwise you're forcing them to also utilize modules. Also define strong code guidelines for the modules and review the build performance metrics so that you know that whatever you're doing is a great choice for your situation. So the current outlook is that we're in 2025. C++20 introduced your modules, C++23 enhanced them with the standard library modules, and C++26 has further refinements to improve tooling support, which is great. But we're still not quite there. You don't really hear about many modules that get written by big libraries. And I feel like if we're talking about modules in a talk, it's mandatory to show this graph from Are We Modules Yet?, which shows that we might be finished reporting all of the popular libraries by 2297, which is a little bit outside of my projected lifespan, but, well, that is a little bit of a chicken and egg problem, because users want to utilize models, but they complain that the tooling is not really quite there yet, and then tooling providers might say that no one really wants to use modules, so there's no incentive for them to support it. Also, the compiler and build system is a little bit uneven, so it's difficult to justify moving a very complicated library or platform into modules. And you see that also libraries will rarely publish modules, so if you want to have something truly module only, it's a very difficult scenario to be in right now. And one of the reasons for that as well, that I feel like, is that the built module interfaces implementations currently are a little bit underwhelming. They're kind of difficult to utilize. They're not really an information hiding mechanism, which is one of the things that I expected out of modules when I first heard about them. And they're not portable, so you cannot really utilize them across compilers or give them to your users. So, but that doesn't have to be forever. The BMIs could be shipped independently, so maybe in the future we land on a way to standardize the ABI for them so that you can just give that to the user and then let them utilize it. The shared libraries could be type safe and also self-descriptive. If you embed a built module interface in a library, it could be very easy for a tool to just look at the library and know what it exports without having to have the header that comes alongside that library. You could also enable very easily something like foreign function interfaces to work. So you could have, for example, Python taking a look at the built C++ library and just being able to immediately hook into those functions without you having to build a wrapper on top of that. And also you could have your cross-compiler compatibility. That's not something that has to be set in stone, has to be different forever, so we just need a little bit of more shared work. And there are many new features that you should be excited about, because some things that were discussed previously, for example, is that preprocessor definitions don't really affect importing headers right now, so it's very useful to have that clarified. You have a paper that forbids macro expansion in the name of modular declarations, which I think will be part of C++ 26, so that also makes it much easier for tools to be able to reason about what is part of a module or not without having to call a compiler to take a look at that. You also have a paper clarifying if you can place main and how you can place main in your named modules, and many other interesting papers that talk about, for example, how to provide pre-built libraries that contains your built module interfaces. And the standard also opens up for some refactorless improvements, which is very interesting. So cpp.include now says that an implementation can treat an importable header, implementation defined, as if it were an import statement. So in the future, you might just have that the compilers have moved far enough in terms of tooling that every old C++ code that was just including everything everywhere might just be cached, and then everything turns into an import. So what is the future of C++? I think this does set a new baseline for shaping the future of C++. You have real encapsulation alongside your build improvements. You have standardized import in semantics. That's much easier boilerplate and migration for someone wanting to get all of these build improvements. And also, now that this is merged, AI can start understanding this and looking into repos that use this to provide help with utilizing modules. And maybe in the future, if you ask AI how to make a hello world in C++, it will just tell you to import std. So we are in a path of making C++ utilize modules more often. So are modules the future of C++? In my opinion, absolutely yes. They are something that is defining and shaping the future of C++ and the future of the standard, so there's no way to escape that. Future code will probably just be written with modules. But are modules the future of your current project? Maybe. I hope to have given you enough information so that you can decide whether it's a good idea for you to be able to start utilizing modules now in your current project, but also understand for your future projects if it's a good idea to start with modules or not. Thank you. We have time for some questions.
You talked about.
Hi, thank you for the talk. You talked about the status of like STL with like compilers. Mm-hmm. Can you tell us about Boost? Because Boost is as important as the STL.
I'm not sure. I didn't get to test the things that were defined in Boost as part of the modules, but yeah, that's something that's outside of the standard, so I limited myself to what is properly part of the standard library.
Okay, so maybe we should treat it as probably important in the private module section, I guess.
For now, yes.
Okay,
that's probably what we do.
Thank you.
There's sometimes something called the Pimpl idiom or Pimpl pattern that's used to hide information. How does that interact with modules?
Yeah, so I showed it before in one of the slides. Okay. And what can be done with the Pimpl idiom here is that if the implementations are sufficiently isolated, you could have a situation where you just build a module that depends on something else, but it doesn't really re-export that dependency. So even if you delete that build dependency and just ship something else, you might just have one file instead of these two files where you have like the Pimpl in one and then the exposed header in the other. So you could have just everything in the same file, which makes it much clearer to utilize.
Okay, thank you.
Hi, I was wondering, what's the story of the interaction between like templates and modules? Like, for example, if I compile a module that exports a template, how is the template stored in the resulting like compiled object? How is it instantiated in things that import the module? Is there any compile time benefits there?
Yes, so as far as I know, most of the compilers were reutilizing the infrastructure that they had for the precompiled headers to make this. So they do compile these templates into a more efficient representation, but they also might just store the tokens that were read from the program, because they might, for example, just choose to implement one version for all of the standard types, like int, float, double, everything like this. But if you need it for a custom type, then you might have to do that yourself. Or the compiler might have to instantiate it again whenever it's importing that module, so it will not be cached.
Okay.
But it's still faster.
Hi, so first question is, why is import stud faster than importing individual headers or all modules?
So as I showed in the graph, in some of the compilers, it just seemed like it could be some variation on my computer that was scheduling it differently. The difference was maybe 1 or 2 milliseconds, so very small. But in other scenarios, it might just be based on the way that they implement the lookup tables for the symbols, for example, and how they implement this structuring. So it's very implementation defined, but different compilers seem to have different results based on that.
Wasn't on your slide something like 0.3 seconds or shorter for import stud and 0.7 for importing everything, which is quite a lot.
That's correctly, yes. Some of the compilers will have a bigger difference.
Okay. And second, if we put all the declarations in the modules, can we like still split the declaration from the definition as with normal, with the previous header implementations?
Yes.
So that would, for example, fix a bit the issue of the compilation graph.
Yes,
we will still be able to compile in parallel. Okay, thank you.
You can still do that.
So I have an answer for the boost question.
That's great.
Boost has made a run at the windmill, as it were, and there's some blog posts by Boost authors about this. I believe there are about 4 Boost libraries that do have module support in their standalone mode, if you will. And then another comment over at the Beeman project, we are actively trying to move modules forward in our project so that you can either use headers or you can use modules.
You should check out the Pimpl project. It's a great project.
Hey, thanks for the talk. I believe this was the only modules talk this year.
Directly, yes, I think so.
Which I appreciate. It needs to be pushed more. My question is, I'm trying to understand what exactly goes in the package that's sent to the user. For the header-only system, you have the headers and the library. What's going to the user in the modules case?
So as of right now, it's a little bit underwhelming. You have to just ship all of your module source files. You can't really just ship the built module interfaces. But that's something that I would hope will change in the future, where you can just compile the module files as if they were a source file, a regular source file, and then you just ship this built, very fast file to the users. But yeah, as of currently, you just have to ship them as if they were a header.
Okay. And one more question is, if I have a module-only library, can it interact with a header library, or do you have to start importing?
That should be possible, but then you get some differences. For example, you might have to change the module code a little bit to change how it's mangled, because the name mangling is affected by being part of a module unit or not. But also, you can go to a header and import a library. Like, there's nothing prohibiting you from going to a header and just adding an import statement in the header. It just means that that will be repeated into every file because it's copy-pasted, right?
So you just need compiler support.
Yes.
As long as.
Exactly.
Thank you.
Hello, my name is Clostel. I have a couple questions. First, if you make a bunch of partitions, is there any change in the build time, or is it pretty much all the same? I can make as many as I like. I shouldn't care about it.
As of right now, you could just make as many as you want. The only difference that would happen is that when they get merged into this single implementation and then this single BMI that gets imported, it would be basically the same.
Cool. And then the second question is, I have a desire to like expand a module potentially with different libraries, like kind of like you do with namespaces. Is there any techniques that you can do to make that happen in modules at the moment?
At the moment, if I understood correctly, it's like the just separation of the namespaces based on the module directly, for example. So
more like, let's say I have like one library that like, let's say is like system, and then I have like storage, and then I have like networking. But those are like subparts, but they're in different locations, and I might not upfront know that those partitions, right? I think those partitions exist. Mm-hmm. So I think right now we have to do module name, and then we have to do import the partition, import the other partitions, correct? Is there any way to make that an open set, or does it always have to be, we have to define everything up front?
If you want to use partitions, you have to define everything up front. But the thing is, modules are composable. So if you don't know that something is part of the same logical component beforehand, you can just define them as different things and then do an export-import in the modules that do utilize those things. So the difference between using a partition or a non-partition is just that you want to expose it outside of that module or not.
Okay, thank you.
No problem.
Great talk, thank you. If I was going to dive in right now and I've got a production project, it's pulling in other libraries, what are the pain points that I'm going to hit?
You will not really be able to utilize all of your third-party libraries as headers, as modules, because most of them do not provide modules. And even the ones that do, for example, if you utilize Cone or VC package, and you use a library like FMT, which does support a module, you cannot import FMT right off the bat. So you need to do that support yourself in your build system.
Okay, and then at that point, if I am still just going and potentially trying to include in, or basically, do I have to expose them myself as modules into the build system, or I can't really like mix and match?
As of right now, you'd have to expose them yourself.
Okay, awesome. Thank you.
No problem.
Hi, Steve Downey. I just wanted to clarify something on one of the last questions. Modules are closed, and that's a design feature.
Yep.
It's like a first-class thing. Not only that, Itanium ABI compilers, Clang and GCC, and Microsoft have agreed that symbols are attached to a module.
Yes.
So you can't change your mind later.
Yes.
Like without recompiling.
Yes, you will break your ABI.
Yeah, it's an ABI thing. And the other unfortunate thing is, and why you have to ship at least the sources for your interface right now. Basically, every compiler flag is this close to being an ODR violation anyway.
Yes.
So it's like, what you're importing is like the parse tree, and it's like, the fact that it still compiles in like 23 and 26, there's subtle differences in what it means. And that's why all the compilers are like, nope, you didn't give me exactly what I was looking for. It's defensive, right? Although Microsoft and Gabi have been working a lot on a portable format, there's still a lot of like limits even to that format without it turning just back into a header.
Yeah, but you could imagine something in the future, like you just have a fat BMI, for example, that just
had a bunch of things in it. Yeah,
exactly.
There are potential things, and the more tightly you can control your ecosystem, the more likely you're able to ship that BMI.
Absolutely.
But you'll probably still have to ship the sources.
As of right now, yes, they did require that.
What it would likely mean is that someone still won't be able to use it.
Yes.
Like they're going to turn, like next year, they'll want to do C++ 29, 26, whatever's next. And suddenly your BMI doesn't work. So it's like, but it wasn't designed to be a mechanism for secret.
Exactly.
Yeah,
that's a very good clarification. When I started looking into modules, that's something that I was surprised about because I expected them to be a mechanism for that. But
yeah, it's like everyone does.
All right. Thank you very much, everyone.